Hello everyone, welcome to the next tutorial of hands-on series on graph neural networks. This tutorial is the part of course Graph Machine Learning Foundations and Applications offered by Department of Artificial Intelligence, IIT Kharagpur. So in this tutorial, we are going to talk about link predictions using graph neural networks. So the link predictions using graph neural networks is going to be the series of two consecutive tutorials. So in this tutorial, I am going to talk about how to create data training for the training of link prediction task using graph neural networks. So first, in the first part, we are going to um, create some dummy data, and I'm going to show you how you can split that data for training and for validation and testing. And we are going to visualize that as well. And after that, we will implement a simple graph neural network model on Cora dataset for link predictions. We will see the implementation of the model, evaluation, training and evaluation. Okay, so let's just start with the part one. So first, uh, we will import the libraries we are going to use. So the PyTorch and the Matplotlib and from the PyTorch geometric, we are going to import to convert the network X graph into the format in which PyTorch geometric takes the input. So from network X, next is train, test, split edges. So this is to create the splits for the training and testing of the edges, and another one is the negative sampling. So we are setting the seed for the reproducibility. Okay, and we are going to create a dummy graph of 50 nodes. So I am going to create this graph using Barbasi-Albert graph. So nx dot Barbasi-Albert graph, n is the number of nodes. Okay, so this is it, and so basically this G will give you the graph. Now we are going to convert this graph into PyTorch geometric data object. So the from network X, we will pass the graph generated using network X, and after that we are going to assign simply like 10 dimensional node features to every node. So data dot x is equals to toss dot random. This is the number of nodes. 50 comma 10 is the 10 dimensional node feature. And after that, we are going to print basic information like the number of nodes, number of edges, number of node features per node, and we are going to visualize the graph as well. Sorry. So we are going to visualize the graph. So this position is to calculate the positions of every node uh, so that you can reuse it, and nx dot draw is will basically plot the graph. So dummy graph for link prediction. So if I run this, so this is your graph. This is the dummy graph what we have just generated. Now we are going to perform the split of edges for train and test. So for that, we are going to use the predefined function in PyTorch geometry, train, test, split edges. And what this function requires is few things like data. Whatever the data object you have created, you have to pass that. The validation ratio, like in this ratio, your validation data is going to be, and the ratio for the test data is 20%. Now, in order to visualize the graph, so some basic syntax. Now we are going to visualize the segregated edges. Okay, so how we are going to do it? So first we will draw like all the nodes with the light gray color. Okay, so from the graph, like all the positions, and we will draw all the nodes with the light gray color. Now draw train edges. Okay, so this is to draw the train edges what we have just created from here. So this data one dot train positive edge index. So this will give you the positive edge index for the training, and nx dot draw network x edges. This will basically draw in blue color, and similarly we are going to do for the test edges as well. So data one dot test positive edge index, which will give you the edge index of the test data positive. Okay, now if you'll run this, so this is the graph you are going to get. So like in the entire graph. So all these are all the nodes with the light gray color, and your blue are your train edges and red are your test edges. So these two edges we have plotted in this graph. So this there is this warning: train test split edges is deprecated. Use transform dot random link split instead. So in the newer version of PyTorch geometric, this has been deprecated. So what we'll do, we'll see like how you can use the random link split as well, because it has some extra features as well. So after this, we are going to discuss how can we split the data using random link split. Okay, so basic information: total number of training edges are 136, total number of validation edges are 9, and total number of test edges are 90. So if you want to plot the test edges, so these are your test edges. Now we are going to write a function to visualize the subset of edges for like more clarity. So this is nothing new. This is just we are going to visualize those subset. For example, train subset, test subset. So from the train edges, we are going to take up to like 100. Okay, so you can take all the edges as well. So I'm just taking 100 edges from the starting. And for the test subset, we are going to take the entire like test data. Okay, and the prepare negative sample for training. So this is just to show you like if you want to train, so you have to provide the negative samples for the training. How you are going to do that? You have to use the negative. You have to like basically create the negative sample using negative sampling functions, what we have already imported from PyTorch geometry. Okay, so now this will provide you the train negative edge index. Now we are going to visualize like all these things. Okay, so if you will run this, the subset of training edges with blue, like these are the from all the training edges, this is the subset of training edges what we have plotted. Subset of test edges, like in the red are the test edges, like all the test edges, and this is the subset of negative edges what we have created for the training. So these are 136. So one subset of these edges has been plotted here. Okay, so now we are going to see if you have. So basically, this is what I wanted to show you in dummy data, what we have created ourselves. Now, this is the exact process what we follow when you are dealing with the like benchmark or real-time data sets. We are going to see in this tutorial moving forward. So now there was a warning of deprecation of this train test link split. So now we are going to see how you can use random link split. So first we'll import this. Okay. After that, the entire thing will remain same as earlier. Okay. So this is just we are creating the graph. Now here we are making some changes. Now split edges for train, validation, and test set using random link split. Okay. So now this is first we are going to define a transform function. So the transform is the random link split what we have imported. Now num val, basically if you will see, the num val is the ratio for the validation. Okay, num test is the ratio for test and is undirected. So if your graph you have generated is undirected, then it's true, otherwise it's false. And add negative train samples. So I mean earlier we have generated the negative samples for training explicitly, but in this you can add negative train samples from this random link split as well. And there are a few more things which has come in this random link split we will discuss. So train data, validation data, and test data. This will transform your data what you have created. So this data is the PyTorch geometric data object. Okay. Now to draw train edges. So now this is if you will run this, you will see the number of nodes are 50, number of edges are 192, and the number of nodes which is 10. So this is your original graph. Okay. So if you will see, the number of training edges created here are 136. Number of validation edges created are 136, and number of test edges are 154. Now, if you'll see, this does not satisfy the ratio what we have given, and given that we had only 192 edges. Okay, so and we wanted like 0.10, not 0.10% as validation and 20% as test. So if you'll take this 10% and 20%, so this numbers does not make sense, right? So what is this? So now we are going to see the what happens in the random link split. So the random link split does not just divide the existing edges into train validation or test sets. It actually creates new edge sets for each split, which can include both positive and negative edges. So this method often creates more edges in total than were in original graph. And why is that? Because it generates negative edges for each split, and it ensures that each split has a balanced number of positive and negative edges. So if you will print the train data, validation data, and test data, so you will see in the train data edge index are this, but if you will see the label index are 68, which is exactly the percentage what we have given. So for the validation, we have given 10%, so 18, and for the test, we have given 20%, so 38. Okay, and for the training it's 68 labels. Okay, so now we are going to see the calculation how we have got this 136, 136, 154, this edge index. Okay, so how this transformation of data happens in the random link split. So the graph has basically 192 divided by 2, 96 undirected edges, as we set validation ratio as 0.1 and test ratio as 0.2. So the validation as labels, so positive, so the positive 96 into 0.1, 9, and negative 9, so total 18. That is what you are seeing here, 18. Okay, and the test 96 into 0.2, 19 positive, 19 negative, so total 38. That is what you see here, 38. And the train edge labels 68, 96 minus 9 minus 19, 68. That is what you see here. Now we will come to this edge indexes. Okay, so the message passing happens into the edge indexes. So in the train, the message passing 68 into 2, that is 136. For the validation, message passing is equals to train message passing, again 136, 136, 136. And for the test, message passing is equals to train message passing plus validation is undirected. So 136 plus 9 into 2, that is 154. So that is what these numbers are. That is how this random link splits generate the edge level random splits. Okay. Now this is again the same what we have generated using random link split. We are going to visualize the subset of edges for more clarity. That is exactly the same. Okay. So because in the random link split here, we have put the add negative train samples is equals to false. That's why I have shown here that you will prepare your negative samples for training explicitly by using negative sampling, this negative sampling function, what we have imported. So again, the entire code remains same as earlier. So if you will run this, so this is the subset of train edges. This is the blue, how it looks, subset of test edges. Now, if you will see, the subset of test edges are like compared to the earlier case, there are a lot more test edges, and the subset of negative edges. These are the negative edges for the training. Okay. So this we have seen using both the methods. One is the older one and one is the newer one, the randomly exposed. Okay, so now we'll see little like the short demo on the link prediction on Cora dataset. So for that, we are going to perform some fixed or like the standard inputs. Okay, so these are these things. So we'll just run this cell. Okay, the torch is not defined. Import torch. Okay. So define the transform for link split. So this is the transform. So t dot compose. What we are going to do? We are first from the transform, we are going to normalize the features. Okay. and then we are going to transfer those to the device, whatever device is available, either GPU or CPU, then the random link split. Okay, over that we are going to perform random link split. Now the validation is 5%, test is 10%, and undirected true, add negative samples false. Okay. So now we are going to do it for the Cora dataset. So we are going to import the Cora dataset as well from the Platinoid, what we have imported here. So from Platinoid Cora and the train data, validation data, test data. Okay, so this is the transform what we are applying. If we will run this, so now we can print and see. So train data, validation data, and test data, how it looks. Now you can obviously calculate and verify these numbers, how these are like these as indexes are coming for the training, validation, and test. And according to the split, these are the edge label indexes. Now you can do your calculation as I showed earlier, and you can verify whether these numbers make sense for you or not. Okay, but if you wanted to just see like how these things look, so from the train data, edge label index looks like this, and edge labels looks like this. Similarly for the test data, and this is the shape what is already written here. This is I just if you want to see explicitly, so you can simply print those things. Now we are going to create a simple GNN model. So the model is GNN link model, and what we are going to use, we are going to use the two layers of GCN graph convolutional neural network, two layers. So con1, con2. Again, this is very standard in channel, hidden channel, hidden channel to output channel. Now this is where we are doing the encoding. So this is the X is your feature, edge indexes are your edge indexes. Okay. So this will basically do the encoding, and in the decode part this is Z. So what this Z basically is all the learned node features which are coming through encode. Okay, and edge label indexes. So what this will do, so from these learned node labels we are going to basically return this. So for every edge, there are two nodes, right? So for the node 1 and the node 2, like for every edge, there are two nodes. Okay, so we are going to take the node features of both the nodes, and at the end we are going to do the sum. And this is to if you wanted to decode like all at once, so this is how you can do that. Now we will initialize our model. So GNN link model dataset.num features 128 is your hidden channels, 64 is your out channels, and this is going to transfer to the device whatever we have. And optimizer is Adam optimizer, and learning rate is 0.01. Again, you can always play with these parameters. Okay, and the criteria is binary cross entropy loss with logic loss. Now, after this, we are going to like write the function for the training. So training with the new negative samples for each training epoch. What does that mean? Simply, we are going to generate the negative samples for the for every training epoch in the train data. Okay. So this is our train function. Okay. So Z, if you will see, Z is equals to model dot encode train data. X is your original node features, and these are the original edge indexes. Okay, so model dot input. So this will return you the Z. Okay, now we perform a round of negative sample for every turning epoch. So this is how we do that. So this will give you the negative edge index, this edge label index, and this will give you the edge label. Okay. Now the output is model dot decode Z. This what we have already generated, and the edge label index. And the loss, again, whatever loss we have defined the criteria, simply it will return you the loss. And this is for the test model dot eval. Again, we will pass all the required thing, and it will return the AUC. So this is area under receiving operating curve. This is what we are returning for the evaluation. So very simple, and now it will just start training. So we are training it for 100 epochs. So at the end, the final test AUC is 0.9180. And if you wanted to look at the final edge indexes using decode all, so this is how you are going to. So this was it. And in the next tutorial, the part two of link prediction with GNNs in transductive versus inductive, we are going to see in the part two, we are going to see different model like graph says as well, and on the more practical and real world data sets. So thank you.